When you first start working with real datasets, one of the fastest surprises is how quickly the number of features can explode, even when the original problem sounded simple. You might begin with a handful of columns, then add one-hot categories, then engineer ratios and interactions, and suddenly you have hundreds or thousands of inputs feeding a model. At that point, it becomes harder to see what is going on, harder to train reliably, and easier to overfit without realizing it. Dimensionality reduction is the set of ideas that helps you manage that complexity without throwing away the signal you care about. The most famous tool here is Principal Component Analysis, PCA, and beginners often hear the name long before they understand the intuition. Today's goal is to make PCA feel like a sensible geometric idea, then walk through the trade-offs and constraints so you know when dimensionality reduction helps and when it quietly makes things worse. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful way to build intuition is to picture each feature as a direction in space. So a dataset with 2 features is a cloud of points on a flat plane, and a dataset with 3 features is a cloud in a 3D room. With many features, you can no longer visualize the room, but the idea is the same. Each row is a point, and the dataset has a shape. PCA looks at that shape and asks a specific question: along which direction does the cloud stretch the most? That direction is the first principal component, and it captures the largest share of variation in the data. Then PCA asks the same question again, but it restricts the next direction to be perpendicular to the first, so you get a second principal component that captures the next largest share of variation without overlapping the first. This continues until you have as many components as original features, but the magic is that the first few often capture most of the meaningful structure. To make that feel less abstract, imagine you have a messy pile of points that forms an elongated oval, like a football shape on the floor. If you wanted to summarize that pile with one number, you would want to measure position along the long axis of the football, because that axis explains the most movement in the data. Measuring along a short axis would miss most of the spread. PCA is essentially finding those axes automatically, even when the cloud lives in hundreds of dimensions, and then expressing each data point using coordinates along those axes. What you gain is a smaller set of new features, called components, that often carry the same overall information as the larger set, just organized differently. What you give up is the original direct meaning of each feature, because the components are combinations of many inputs rather than one-to-one copies. That loss of direct meaning is the first major trade-off you should keep in mind, especially in security-related work where people care about explanations. If a feature is something like failed logins, it has an obvious interpretation, but a principal component might be a blend of failed logins, time-of-day indicators, device fingerprints, and dozens of other columns. The component might predict outcomes well, but it is harder to explain to a non-technical stakeholder why the model flagged an account if the key input is component 3 rather than a human-understandable signal. This is not a reason to avoid dimensionality reduction. It is a reminder that you should be honest about what the model is optimizing for. In cloud security, analysts often need to justify decisions like blocking access or escalating an incident, and losing interpretability can create friction or mistrust. So the thoughtful approach is to consider whether your goal is pure performance, operational stability, or explainable reasoning, because PCA shifts that balance. Another important idea is that PCA is driven by variance, meaning it pays attention to directions where the data varies the most, not necessarily directions that are most predictive for your target. Beginners sometimes assume the most variation must be the most important, but that is not always true. A feature can vary a lot because it captures harmless operational noise, like fluctuations in benign traffic volume, while a subtle but critical security signal might vary only a little, like a rare but meaningful privilege escalation pattern. If you reduce dimensionality too aggressively, you can keep the loud noise and discard the quiet signal, because PCA does not know which variation matters for your prediction task. This is why dimensionality reduction is not a universal pre-processing step you apply automatically. It is a modeling choice that should be justified by your specific problem, your evaluation method, and your tolerance for losing small but important patterns. The role of scaling becomes especially important here because PCA depends heavily on the relative scales of your features. If one feature has values in the thousands and another has values in fractions, the large-scale feature can dominate the variance purely due to units, not importance. Standardization is often used before PCA to put features on comparable footing, so variance reflects structure rather than measurement scale. This is also a place where beginners can accidentally introduce leakage if they compute scaling parameters using all data rather than training data only, because even small distribution differences in held-out data can influence the transformation. A careful pipeline treats scaling and PCA as training time learned steps, then applies them unchanged to validation and testing. In cloud environments, data distributions can shift due to new deployments, new user populations, or seasonal usage patterns, so the stability of these learned transforms matters. If the transform is built improperly, you can end up with components that look stable in development but behave unpredictably when the system changes. It also helps to understand what PCA is doing mathematically at a high level without getting lost in equations, because that explains why the method behaves the way it does. Under the hood, PCA is closely related to singular value decomposition, SVD, which is a way of factoring a data matrix into simpler pieces that reveal its dominant structure. You do not need to compute SVD manually to benefit from the intuition. The data can be represented as a combination of patterns, and the strongest patterns come first. When you keep only the top components, you are saying that the weaker patterns are either noise or not worth the complexity. This is why people often talk about the explained variance ratio, which describes how much of the total variance is captured by the first K components. The beginner-friendly takeaway is that PCA is a compression method. It keeps the strongest structure and discards the rest, and you must decide whether the discarded part was noise or signal. That decision about how many components to keep is one of the most practical constraints, because there is no universal correct number. If you keep too few, you may lose critical information and underfit, meaning the model cannot represent important distinctions. If you keep too many, you may not reduce complexity enough to gain the benefits you wanted, such as faster training or less overfitting. A common approach is to look for a point of diminishing returns where each additional component adds only a small amount of explained variance. But even that can be misleading if the prediction target depends on subtle structure. In security and reliability settings, rare events matter, and rare event signal can live in low variance directions that PCA might consider unimportant. So a thoughtful approach combines variance-based intuition with performance evaluation on your actual task, while still respecting time ordering and leakage constraints. You are not choosing components to make a chart look neat. You are choosing a representation that should support trustworthy predictions. Another constraint that often surprises beginners is that PCA creates components that are linear combinations of the original features, which means it can only capture linear structure in the feature space. If the meaningful pattern in your data is curved or involves complex nonlinear relationships, PCA might not compress it well. The method can still be useful because linear compression can reduce noise and make learning easier for later models, but it will not magically solve nonlinear structure by itself. This is where you might hear about nonlinear dimensionality reduction methods, but the core lesson remains. Every reduction method has assumptions, and those assumptions should match the data's shape. In cloud security datasets, behavior can be highly nonlinear, such as sudden threshold effects during attacks, or combined conditions that produce risk only when multiple signals align. PCA can still help by smoothing redundant features and reducing multicollinearity, but you should not expect it to extract every subtle pattern automatically. Dimensionality reduction is often motivated by the curse of dimensionality, which is the idea that high-dimensional spaces behave in unintuitive ways that can make learning harder. As dimensions increase, data points tend to become more spread out, and distance-based notions like nearest neighbors can become less meaningful because everything starts to look similarly far away. Even for models that are not explicitly distance-based, having many features can make it easier to fit noise, because there are more degrees of freedom to capture random quirks. Reducing dimensionality can improve generalization by limiting that freedom and emphasizing shared structure rather than individual tiny variations. At the same time, reducing dimensionality can make it harder to detect unusual behavior if the unusual behavior is rare and gets averaged out in the compression. In security, you often care about the unusual, so you need to be careful that the reduction step does not flatten the very anomalies you want to detect. Thoughtful reduction means you are clear about whether you are trying to model typical behavior or detect exceptions. There is also a subtle operational constraint. PCA produces a representation that is tied to the training distribution, and when the world shifts, the meaning of the components can drift. If a cloud provider changes logging formats, if a new service generates new kinds of traffic, or if user behavior changes due to policy updates, the direction of maximum variance can change. That means the component axes learned last month might not describe this month's data as well, and the compressed representation can lose fidelity. This does not mean PCA is fragile by default, but it does mean you should treat it as a learned artifact that may need monitoring and retraining. Beginners sometimes assume pre-processing is fixed and permanent, but in practice, transformations can become stale as the data-generating process evolves. In data pipelines that support cloud security analytics, maintaining consistency across time is critical because a silent shift in representation can look like a sudden model degradation without an obvious cause. Another trade-off to think about is how dimensionality reduction interacts with feature selection, because these are different strategies with different consequences. Feature selection keeps a subset of original features, which preserves interpretability and direct meaning, but it might discard useful combined structure that emerges only when features are considered together. PCA keeps combined structure but replaces original features with mixtures, which can reduce multicollinearity and noise but makes interpretation harder. In some cases, feature selection is preferable because it keeps you grounded in the domain, especially when you need to explain why a decision was made. In other cases, PCA is preferable because the original features are highly redundant, like many correlated metrics that all measure similar activity at different resolutions. A thoughtful workflow often tries to understand redundancy and correlation first, then chooses whether to remove features directly or compress them into components. The wrong move is to compress blindly and assume it is always better, because that can hide problems you would have noticed at the original feature level. It is also worth addressing a beginner misunderstanding about what dimensionality reduction does to privacy and security, because people sometimes assume that converting features into components automatically anonymizes the data. While PCA changes the representation, it does not guarantee that sensitive information is removed, because the components can still encode the same underlying signal, just in a mixed form. If the original data contains identifying patterns, those patterns can still be present in the compressed features, and a determined attacker or analyst might still be able to infer sensitive attributes. So you should not treat dimensionality reduction as a privacy control, even though it can sometimes reduce direct exposure of specific columns. In cloud security contexts, you may be handling logs that contain user identifiers, device identifiers, or behavioral signals that are sensitive, and those concerns require explicit privacy and governance controls. The safe mental model is that PCA is about learning efficiency and representation, not about compliance or de-identification. Mixing up those goals can lead to false confidence and risky handling practices. When you decide to use dimensionality reduction, the most important discipline is to keep your evaluation honest and your pipeline consistent. The components must be learned on training data only, and the transformation must be applied consistently to anything the model will see later, including validation, testing, and future production data. You also need to be careful about time-aware splits, because if your dataset spans time, learning components from future periods can leak future distribution structure into the past. This is not the same as leaking labels, but it can still create unrealistic performance because the model benefits from knowing the future shape of the data. In real systems, you would not have that knowledge at training time. Thoughtful dimensionality reduction respects the same rules as modeling. You simulate the real-world information boundary, you avoid peaking, and you confirm that the compressed representation supports stable performance across the time periods you care about. That kind of discipline is what turns a clever technique into a trustworthy one. By the time you finish this topic, you should be able to explain dimensionality reduction as a structured trade between complexity, stability, and interpretability, rather than as a mysterious math trick. PCA provides a way to rotate your feature space, so the most important variation comes first, letting you compress many features into a smaller set of components that often preserves the dataset's core structure. The trade-offs include reduced interpretability, the risk of discarding low variance but important signals, and dependence on proper scaling and training-only fitting to avoid leakage and instability. The constraints include linearity assumptions, sensitivity to distribution shift, and the need for time-aware handling when the data evolves. When used thoughtfully, dimensionality reduction can make models faster, more stable, and less prone to overfitting by removing redundancy and noise. When used carelessly, it can hide critical signals and produce performance that does not hold up in the environments where decisions actually matter.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.